All right. Well, I think we're going to get started here. Good afternoon, everyone. Really happy to have everybody here online virtually to join us today. I hope you're all staying safe and healthy. My name is Sean Porse, and I am the Geothermal Manufacturing Prize Lead for the Department of Energy's Geothermal Technologies Office. I'm really thrilled to be here today with all of you to kick off our afternoon's dynamic set of sessions on all things geothermal and additive manufacturing. Before we do dive into this afternoon's agenda, I do want to first take an opportunity to thank both the Nation of Makers team as well as National Renewable Energy Laboratory team for really making most of what we're doing today here possible. So thanks very much. Now I'd like to kind of go into just a bit briefly on an overview about what the Geothermal Manufacturing Prize is all about before we get into our sessions on Geothermal 101, pulling energy from the earth. So the Geothermal Manufacturing Prize is a set of 4 contests seeking to leverage additive manufacturing innovations for pushing the boundaries in how we design, fabricate, operate geothermal tools, equipment, and componentry. Along the way, we're going to be offering a total of $4.65 million in incentives for competitors, $3.25 million in cash, $1 million in technical vouchers, and up to $400,000 in field testing costs that can be used by grand prize winners to bring their concepts to the field for testing. And not only that, this program is supported by the American-Made Network. It is a community of over 130 energy incubators, investors, universities, national labs, and others across the United States to help participants achieve their goals. I will briefly say that in addition to sort of participating as a direct competitor in this prize competition, anybody can also apply to join the American-Made Network. So if you feel that you have technical resources or insights that would be useful and to collaborate with correct competitors of this prize or other DOE prizes, I encourage you to check out our website to learn more about how you can become a part of the American-Made Network. So we're gathered here today to sort of talk about additive and geothermal and why exactly would we think about those two things sort of being paired together. Well, as we'll go into here in today's session as well as in sessions after that, the tools and equipment and components that we use in geothermal are a veritable wilderness of types and functions needed to be able to drill, interrogate, and monitor as well as operate in geothermal environments from any amount of time from days to months to even years. Examples can include intricate flow passageways, complex assemblies, as well as having to engineer tools to meet compact form factors such as well bores. And this can be expensive and challenging to manufacture due to the specialized geometries, the materials that are required in order to manufacture, and then the relatively low manufacturing volumes associated with the current U.S. geothermal industry. But this is really where we feel that additive manufacturing is coming into play. We're excited to explore how additive can push the envelope in part because of the promising innovation examples. This technology approach continues to provide for a number of other industries here in the U.S. and abroad. We could think of examples from automotive, from aerospace, and from other clean energy sectors. And what's fantastic about the group of experts we have here today is that they'll really be able to provide some really great insights on those analogous industries and how additive has really improved the design and functionality of tools in those respective industries. So just as, overall, what we're looking to do here with additive is to use it to incorporate and reduce the design and manufacturing lead times associated with building geothermal tools. We want to be able to save money and materials along the way. And ultimately, we want to be able to improve the performance necessary for operating in geothermal environments. On the right-hand side of the screen, you see a original as well as a topologically optimized part. And this is kind of a preview of a very exciting lightning talk that will be happening later today from Jin Su from Sandia National Laboratories. The original part there is a rotor piece of a percussive hammer drill and the motor that drives that drill. And the original part was built and manufactured in a solid state design. And the optimized part below is topologically optimized in a way that additive manufacturing can provide, where subtractive and other conventional means could not. So it's exactly this type of an idea that we're looking to help build a dialogue and converse around today in order to hope to be able to spark some collaboration and some great ideas to enter and compete within the competition. So speaking of the competition, we're going about cultivating these ideas through 4 contests, the Ready, Set, Make, and Geo contests. There are 4 escalating challenges, and along the way, we're walking the path of manufacturing innovation from concept, which is part of the Ready phase, to developing your design in the set phase, to prototyping in make, and finally in the penultimate phase in geo, building a proof of concept that can then be tested at geothermal type conditions. And 2 grand prize winners are going to walk away with $500,000 in cash and up to $200,000 each to put towards testing their prototype in the field. Currently, we are here at the top of the wellhead here in the midst of the ready phase, and we have applications open, and you can submit an application as an individual or a team through August 26th this summer. And of course, all of this type of information and more is always available at americanmadechallenges.org/geothermal manufacturing. But now I want to transition to bring in our experts for the hour on Geothermal 101, pulling energy from the earth. I'm really thrilled to have Kate Young, who is the Geothermal Program Lead for the National Renewable Energy Laboratory, as well as Jamie Beard, the Executive Director for the Geothermal Entrepreneurial Organization at the University of Texas at Austin. And they're going to be providing some of their thoughts on geothermal energy, including what it is its value to the U.S., and what are some of the challenges and intern opportunities that are going to really require technology and manufacturing innovations like additive to help solve. First, I'd like to hand it over to Kate. So Kate, let me know, and hopefully you can share your screen. Kate, let me know if you need me to help you with that.
Sorry, I obviously just needed help with my mute button. So I apologize. This is Kate Young. I'm the Geothermal Program Manager at the National Renewable Energy Laboratory, and I'm here to give you an overview of and a little bit of background on geothermal. Let me try to expand my screen here. All right, so first, what is geothermal? Geothermal is looking at and utilizing the heat from the earth. And the earth is hot enough. It's as hot as the surface of the sun. It's even at only 6,500 kilometers from the surface. So it gets even hotter, up to 11,000 degrees at the center of the earth, at the core of the earth. And so we're utilizing this heat in the shallow areas of the earth, in this shallow crust, to make heat both for electricity generation as well as for direct use, for heating homes and for industrial processes and things like that. So traditional geothermal projects need 3 things. We look for heat in the earth, and we also look for a connected fracture network that exists naturally in the subsurface. And then within that fracture network, there's fluid that exists. And so the goal is to drill into this fracture network, extract these warm fluids up into a power plant, generate steam, which turns a turbine, cool that fluid back down, and re-inject it back into the earth to be reheated and continue that cycle. This shows the amount of geothermal in the world. There's a total of over 15 gigawatts as of the end of 2019 deployed worldwide, and the US is currently the leader in this deployment with over 3.5 gigawatts of geothermal deployed. Many of you may have heard of places like New Zealand and Iceland having high levels of geothermal deployment. And from a percentage of energy that they provide, they are certainly some of the global leaders. But in terms of actual gigawatts deployed, the US is still the leader in these areas. And where is this deployed? Currently, it's deployed mostly in the Western US. You can see these data are a bit old. It's from 2015, the last time that the Geothermal Energy Association put this data together. We are in the process of updating these data as we speak, but this is as of 2015, and you can see it's mostly in the Western US, where you think of things like mountains and hot springs and geysers, as well as in Alaska and Hawaii. Now, the U.S. Geological Survey put together a resource assessment back in 2008, looking at what the geothermal potential is in the U.S. And so you can see The black dots there show the locations where they've identified specific areas for development, and they've identified 9 gigawatts of potential there. And the other areas show that there's likely many more areas for development, and so they've estimated an additional 30 gigawatts of potential of this traditional hydrothermal geothermal development. And what do we use it for? All sorts of different things, and it depends on the temperature of the resource. And so the hotter the temperature, the more things that we can be using it for. But here at the lower temperatures, many of you may have heard of things like geothermal heat pumps, and you may see that that pulling these warmer fluids from the subsurface can be used for things like fish farming and greenhouses and food processing. It can be used for building heating and cooling. District heating systems are very common all over Europe, and we do have some in the US as well. And then as you get into warmer temperatures, we start using them for industrial processes. You can see in these orange examples here, everything from cement and aggregate drying, fabric, paper pulp processing, and even into hydrogen production. On the left side here, you can see power generation, and we can do that even at low temperatures as well, down to 95 degrees C, and all the way up into these higher temperatures as well. So there's a lot that we can do with the energy from the earth. And so part of the challenge we have for you today is helping us access this heat. And so what do geothermal costs look like? I wanted to put this slide up because it shows geothermal costs in different areas. And so if you look in the brown, this is really the North American prices. And looking at things, it's at less than 10 cents per kilowatt hour. But what you'll notice is that as you get to these larger circles, these are the larger production areas, we're also getting into hotter temperatures. And so there is the ability to reduce these the cost of projects as we get to larger and hotter resources. And so that's another challenge we'll be talking about today, is helping us dig deeper so that we can get to these hotter and larger resources. And so why do we talk about geothermal? Why are we interested? And there's a lot of really exciting reasons, and we'll go through these in a little bit of detail here. And so the first is that it boosts the local economy. And so a typical 20 megawatt geothermal facility pays a lot in local property taxes and in annual royalties. And these go back directly to the communities in which they're operating. They help pay for schools and other community events and other community programs. And you can see that compared to even other forms of energy and energy development, that these payments to the local economy are far greater per 1,000 homes powered than any other resource out there. They also create long-term wage-earning jobs. So in addition to having many construction jobs, temporary construction jobs, there's also long-term operation and maintenance jobs, which is really a boost, again, to the local economy. About 2.13 long-term jobs per megawatt installed. And again, being able to compare this to other types of energies, this really shows that geothermal projects are a big part of the communities in which they operate. So there's also very low impact for geothermal projects, and this is both in its emissions as well as its land use. In the upper left, you see a picture. This comes from the Department of Energy, and this is a 30-year operational emissions from a closed-loop geothermal power plant. And you can see that those emissions are less than all of the emissions burned in a single gallon of gasoline from a car. So these emissions are really, really low. It has a very big impact on the ability to reduce carbon emissions, as well as other emissions relative to other power and electricity sources. As well, geothermal also has a very small footprint. So the amount of land use that a geothermal power plant takes up per kilowatt or megawatt or gigawatt of energy produced is significantly smaller than other types of electricity generation. And you can see that when you drive by on a highway, you may blink and miss seeing a geothermal power plant. Another advantage is it's always available day or night. So you can see in this image in the bottom left, we can see a cloudy day, not much wind blowing, and yet geothermal is still operating regardless of the weather, regardless of the time of year, the time of day. And that means that geothermal has a high capacity factor. That means if you build a 20 megawatt geothermal plant, it's available 90% of the time. If you build a 20 megawatt solar or wind plant, it's only available to produce that amount of power 20 to 45% of the time. So for the small footprint, it packs a big punch. And then on the right here, you can see this is a little bit more complicated curve, a complicated diagram, but this line right here represents the amount of energy demand needed by the grid, and it's the net energy demand after renewables. And you can see as more and more solar is added to the grid, the net energy demand in the middle of the day starts to go down, which means we have this inconsistent curve. And so the other generation sources need to make up this energy demand. So we need to make up more in the morning, and then it needs to drop off during the day, quickly ramp up in the evening to make more power. And so one of the benefits of geothermal is that we can provide consistent power throughout the day without causing these inconsistencies throughout the day in the net balance of energy needed. We can also provide flexibility and be able to ramp up and down to meet these variable energy demands throughout the day. And finally, because of those curves, one of the advantages of geothermal is that it is available, because it is available throughout the day, that each additional unit of geothermal that you add is valuable to the grid. So if we've got 5% of the grid being supplied with geothermal, it's just as valuable as if we have 30%. But you can see that as you add an increasing amounts of these other variable renewables, that each increasing amount becomes less and less valuable. And that's again because it's only providing power during certain parts of the day. So as you add increasing amounts of solar on the grid, each incremental amount is less and less valuable. Some of the other things that are beneficial to the grid is that geothermal can provide this flexible capacity, can ramp up and down, and it can provide services to the grid that are complex to explain, but things like frequency response, spinning and non-spinning reserves, voltage control, inertia, black start capabilities, and fuel security. So there's a lot of benefits to geothermal, and how much geothermal is really out there. And so the Department of Energy recently worked with the consortium of its national labs to put out a geovision study. This came out about a year ago in May of 2019, and it looked at different things. Two of the challenges that I'd like to discuss with this group today include development costs. And so the first is in drilling. The development costs, about 50% of a project is consumed by building the power plant, and the other 50% is in the well field. And this is what Jamie's going to be talking about with you today in more detail. But you can see this is a curve showing that as you get deeper, the wells get more and more expensive. And one of the things that this study looked at was how can we reduce these costs for drilling the well. And if we reduce those costs, what impact is it going to have? So that's challenge number one. Half of these well field costs come in drilling, and the other half comes in materials, things like casing and cement. And so we'll be going over those with you today. And one of the shifts that we talk about is, can we go to deeper and hotter wells? So really, I brought this up in the past, but looking at if we go to deeper wells, we get to hotter resources. And when we do that, the energy density per well goes up. You can see oil and gas wells have an average of 10 megawatts of energy per well. Traditional, conventional geothermal, it looks at about 7 megawatts per well. And as we start to go deeper and hotter, we're looking at upwards of 40 to 50 megawatts of energy per well. And when we do this, when we increase the temperature and we increase the depth, it means we need to have fewer numbers of wells per per project. So you can see these are both about 100 megawatt projects. The one on the left has 42 wells at 200 degrees C to produce just over 100 megawatts. And the project on the right only needs 3 wells. And so if drilling makes up a significant portion of our project and we can reduce the number of wells we're drilling, that can have a significant impact on those costs. And we saw that in the levelized cost of electricity cost comparison. So our first target, cheaper, deeper, and harsher environment tools. And Jamie will be getting into that more in her next talk there. And so the next challenge we have is that it's a location-specific resource. So looking at this USGS map that I brought up earlier, you can see number one that it's mostly in the U.S. and number two that it's a point source location, and that's because we're targeting, remember, those fractures and that fluid network. And so if we have a second paradigm shift here, and instead of needing all 3 of these things, we just look at 2, the heat actually exists everywhere beneath the surface of the earth. And so what we're really looking for is how do we bring that heat to the surface? So in traditional systems, we have this fracture and fluid network, but the Department of Energy, the US Department of Energy is looking at other ways to do this. And so this diagram is from their GeoVision study, but you can see here, this is an example from these of the natural fractures with the fluid in the subsurface and bringing those to the surface. They can be used either to make power, as in these 2 examples, or for direct use, as we discussed. But if we can figure out a way to get that heat exchanger and bring that heat to the surface in a different way, then we have opportunity to use this anywhere throughout the US. And so you can see this is a graphic here. One of the projects that the Department of Energy is working on is a project called FORGE, the Frontier Observatory for Research in Geothermal Energy. And its focus is on developing these enhanced geothermal systems, or EGS systems, where they're going down and creating this fracture network and circulating the fluid on their own through the subsurface so that this can be done anywhere throughout the US. Another way that, that some companies are looking to do things is through closed loop geothermal systems, or something called advanced geothermal systems. And so in this example on the right, they're going down and circulating through hot rock and bringing it directly up to the surface. And so I believe Jamie is going to talk more about both of these opportunities and ways that this manufacturing prize may be able to help. And so this target number 2 is how do we do geothermal anywhere? And what happens when we do that? And so these are results from the GeoVision study. If we can lower the costs and we can do the geothermal anywhere, overcoming those 2 challenges, we can increase deployment by 10 times in the US. And so you can see this red line here shows a business as usual scenario with no new improvements. We increase from today's 3.5 gigawatts up to 6 gigawatts of deployment by 2050. And if we can lower these costs and do geothermal anywhere, you can see that amount goes from 6 gigawatts up to 60 gigawatts. And that amount is relatively conservative if everything stays the same. If there's fluctuations in other competing electricity prices, in this example shown in the screen, we've got high natural gas prices. You can see that the potential for geothermal deployment can increase even further, up to 26 times. And even beyond. And so what does that look like? You can see here on the right-hand side at this, that geothermal can make up to over 20% of the US geothermal, or the US generation, and this is for power by 2050, and even a larger portion of the direct heating needs for the US. And so what does that mean in terms of market impact? Faster drilling, lower costs, it relates to cost savings and increased market competitiveness. So as we talked about, that's 50 gigawatts. But what does that mean? Gigawatts are sometimes a hard unit for people to comprehend. And so that's an extra 1,000 wells per year, every year in the US alone for the next 30 years. And so if you compare that to the current geothermal drilling rate of less than 10 wells or so a year, that's a significant increase if we can overcome these barriers. And though it's still shy of the 15 to 20,000 oil and gas wells we drill in the US each year, these geothermal wells still will take longer than oil and gas wells. And so hour for hour, drilling these geothermal wells will be a comparable number of millions of hours per year in drilling. So there's huge potential for growth in this area. And so that's the conclusion of my presentation. I don't know if we're taking questions now or if we're going on to Jamie.
Thanks, Kate. Yeah, well, folks, if folks want to hold questions, we will actually have a chance at the end here before the break in order to discuss questions with both Kate and Jamie. So thank you, Kate, very much. That was a fantastic presentation. I want to invite Jamie Beard from UT Austin to take the virtual share of the screen here, and we welcome and look forward to her presentation.
Hey everybody, can you hear me and see my screen?
We can.
All right, let's do it. So I'm not able to drive. Can somebody give me, there we go. All right, so I'm Jamie Beard. I'm with the University of Texas at Austin, and I'm running a program called GEO, which the goal is to create an innovation ecosystem for geothermal in Texas and to draw the interest of the oil and gas industry in solving geothermal problems, in particular drilling problems associated with geothermal energy. And so I'm particularly interested in characterization and evaluation, drilling, and completion technologies that can translate from oil and gas into the geothermal space. And today we're going to do a quick overview, Drilling 101. This is just a drilling foundation class for folks that don't know how wells are drilled. And I think this could be a good overview for folks from the maker community that may not know the basics of how we do this now, both in the oil and gas and geothermal industries. And so I will draw comparisons as we go between the methodologies, and we'll talk about that. For the drilling experts of the world, this is probably, you could run circles around me easily in this topic. So in the question and answer session, please feel free to submit ideas or thoughts based on your specific knowledge of drilling. All right, so let's get started. Drilling fast saves time. It's called rate of penetration in the oil and gas industry. You want to get in and get out when it comes to drilling your wells as quickly as possible, because rigs are very expensive. Depending on what type of rig you're running and depending on what type of kits you have on site, rigs can cost, $20, $40, even $80,000 a day. And when you have problems, they get even more expensive because you have downtime. So, and that's the second point here is, while we want to drill faster, we also want to reduce tool failure. And those things are actually related, but adversely. So when you drill faster, you actually cause tools to fail more, right? So you actually double the problem when you want to go fast, because you also want to get your tools to last longer. So when you have a tool failure downhole, it's called tripping. You have to stop your drilling operation. You have to back everything out. While this is happening, everybody's kind of hanging out. You've got rig crews that are idle. You have time that's passing, and you're paying leases on not only the rig, but also the tools that you have on site. So, tool failure and downtime is a big deal. Tripping can take, an entire day and cause, an $80,000 loss easily if you have a tool failure. So you really want to, we really want to push and harden the tools so they fail less. So what are we looking at? We want tools to go hotter. We're looking at least 200 C. Hotter the better though for geothermal well economics. So 350 C, go for it. The sky is the limit. We're looking for tools that perform well under extreme shock and vibration conditions, which are encountered in drilling, and I'll explain why in a bit. Also high pressure situations and corrosive environments. So why do we care, and why is this cool? Kate touched on it. I want to drive it home. This is the US at 10 kilometers deep. Anything above 150C is pretty cool when it comes to geothermal development. And so look at what we have here, right? If we're able to drill quickly, cheaply, and drive up tool capabilities in high temperatures, you know, we could drill for geothermal energy anywhere in the United States, just about, right? And so that's what you're looking at here, just an enormous resource and a very, very exciting opportunity to make a big difference when it comes to the clean energy portfolio of the United States. All right, so how are wells drilled? Vertically and directionally. So you see on the right here, a vertical well. This is how, for most of the history of drilling, wells were drilled, both in oil and gas and in geothermal. It's mechanically pretty simple. It doesn't require a whole lot of high-tech equipment. Most systems that are used are mechanical systems. And oil and gas did this for a long time until a couple of decades ago when there were some quick and very impactful technology developments. It's worth noting that geothermal still largely uses vertical. And the reason for that is because the tools that enable this, so on the left-hand side here, you see this is a directional drilling diagram, and that turn is enabled by a flourish of technological innovations that are not currently enabled in ultra high temperature, shock pressure, et cetera, that you would encounter in geothermal wells. So geothermal drilling is largely stuck here, and we'll talk about why that's a problem in just a second. All right, so this is a typical EGS plant, so enhanced geothermal systems. Kate touched on it. It's a scalable geothermal concept, which is really cool, meaning we could do a little bit of characterization work on the surface to make sure we've got a good site, but pretty much you could aim to do these anywhere under the right conditions. But these are vertical wells, right? So you drill a well, you've got the well on the left. That's your injection well. You drill a producing well. You engineer a fracture network in the subsurface, leveraging existing fractures and using stimulation techniques that are utilized in the oil and gas industry largely. And you circulate a fluid. And here's your power plant. You produce energy. This is EGS phase 1, really cool in development. A lot of work has been done in this area. EGS phase 2, which is developing, is you see here this familiar turn, right? So it would require directional techniques. You're going to have to know how to steer your bits. You're going to have to know where you're going. But if you do that, you can drill horizontal and parallel wells and create fracture networks in between them. And so you have an injector. The water goes in, it filters down, gravity pulled into this, into your producing well, and you go up and there'd be a power plant here on the surface to produce energy. So this is something that can be enabled directly. It's really on the bleeding edge of EGS. There are a few startups out there that are trying to do it, but we really, really need to harden directional drilling tools to make this happen. And this is the frontier of really complex drilling, the AGS, Advanced Geothermal Systems, or closed loop systems. There are some startups out there trying this now as well. It's largely, it's largely limited right now by temperature limitations and directional drilling tools, because you really, really are relying on directional drilling techniques to drill something this complex. You've got to know where you are so you don't have intersections between the wells, et cetera. So, you know, in order to push these types of concepts into the really high temperatures, we're going to have some quick developments in tools. So what are we talking about? Well, before we drill a well, we want to make sure that the site is interesting. So we want to do some characterization work. It's essentially making a subsurface model. And to do that, we need to understand where the temperature is and how deep it is. So geothermal gradient, natural fractures and fault networks, that's really important for EGS. We definitely don't want to build an EGS plant on a fault because it can create seismicity. So we want to understand that very thoroughly before we build. We want to know the presence of water and formation types. The reason that's important is because some formations are much, much more difficult to drill into. And so you want to pick the low-hanging fruit and the easier formations to make the wells. And you want to know the stresses and pressures in the formation before you start drilling. For the drilling process itself, we need to know everything we can while we're drilling, and ideally in real time, right? So we want to know where our bit is when we're drilling in terms of coordinates. We want to know where we're going. We want to know the conditions it's encountering. So we need to know temperature, pressure. We need to know how much shock and vibration the tool is encountering. The real-time part's important because it will allow directional drillers to make adjustments to avoid catastrophic tool failures, and we'll talk about that as well. We need to be able to do directional turns, and we need to be able to power all this stuff downhole, and we'll talk about that in a case study at the end. Finally, another important piece, after you drill a well, you're going to have to operate it, right? So you've got that whole piece of circulating your fluid through the system. And it seems simple, but there's actually a complex set of metrics that you need to know in order to optimize that system. So you need downhole sensors that are embedded for really long periods of time under really horrible, harsh conditions, including really high pressures. So sensors that can survive that for the life of the well, which is not an insignificant ask. We need to be able to monitor in EGS systems how the fractures are evolving over time. One difficulty that EGS systems encounter are what's called short circuits, where over time fractures will widen to a point where you can lose your reservoir. So the water or the circulation fluid just falls out of the bottom due to a short circuit. So we need to be able to monitor to see why that's happening, how it's happening, where it's happening, and repair it if possible. So, so this is after you drill. There's still a lot of opportunity for technology innovation. So let's do a quick overview of how we drill. I'm going to fly through this, so we'll have plenty of time for questions. But oil and gas and geothermal have diverged in their methodologies over the last 3 or 4 decades, largely as a result of innovations in directional drilling technologies. So I'll touch on that. But in general, when you drill, you have a drill string. The drill string includes the bit, which is here. And you've got the BHA, which we'll talk about in a second. It's called a bottom hole assembly. It's where all the cool technology is. You have a drill collar, which is essentially the weight on the bit. It's a really heavy pipe. And then you have the drill pipe. The bit crushes and cuts rock. When you're digging a hole with a shovel, for instance, you end up with a pile of dirt, right, beside your hole. And when you're drilling, you have that same problem. So you have to figure out a way to get the dirt that you're cutting out of the hole. And the way that's done in drilling is through a mud circulation system, where mud is pumped. Let's go back. Mud is pumped down the center, the hollow center of these tools. It's ejected from nozzles in the bit, and then it picks up your cuttings and it forces them out of the annulus of the well and back to the surface. And then the mud is cleaned and pumped back down hole. So that's how drilling is done in basic terms. Drill pipe is layered in 30-foot sections behind the bit. So as you drill and you get deeper, you lay sections of pipe as you go. And that's largely why we need a derrick, right? So the quintessential drill rig, the reason you've got this tower here is because it's a pipe handling system. So you have all your pipe stacked here, a bunch of pulleys pull it up and they store it here. And as you drill and you get deeper and deeper, they put a new piece of pipe and you keep going. There's hundreds of pieces of drill pipe that get put together to reach total depth of a well, or what they call TD. And then the last drilling step is casing and cementing, where after they drill, they go back in with a larger piece of pipe called casing, and they lay it down in the hole and they cement it in place. And this helps with wellbore integrity, but it also isolates the well from the formation, so you don't have water intrusion or pressure problems with the system. All right, so bottom hole assembly. So this is where all the action happens, particularly in directional drilling. You have your drill bit here, like we saw in the prior diagram. And then depending on what you're trying to do, what kits you have on site and what technologies you want to use, there's all sorts of technologies that are placed together, threaded together in the BHA. And so typically you'll have the bit. The bit can be, it can be a rotary steerable or RSS system, or a dumb bit, a not smart bit. I'll go over that in the next slide. And then you've got a motor that drives the bit typically. Then you'll have an MWD and a power system for the MWD, which is typically batteries or a downhole generator or turbine. An LWD, sometimes if you want even more information about your formation. And so all of these tools are stacked together. And then at the very end of your BHA, you'll have a transition piece and then your drill pipe. So that's, and this piece leads the way as you drill. It encounters the worst of the conditions, and it's also the most delicate. And that's where the failures lie, and the idea of hardening tools comes in. All right, so when I mentioned basic or intelligent on drill bits, there's the type that you can drive from the surface. So they are mostly mechanical, or there's the really intelligent ones that you can pre-program to go places and just watch them as they go and monitor. Those are called rotary steerable systems. Really cool, would be great to enable rotary steerable systems in higher temperatures. They have a lot of sensitive electronics, and right now it's not possible to use them in geothermal wells. Motors, same thing. All of these, from the MWD to the mud pulsar that sends data to the surface in the MWD, telemetry systems, logging while drilling, all of these systems have weaknesses in high temperature and shock and vibe environments. And we'll consider one of those weaknesses in a case study in a second. Right now in directional drilling and oil and gas, most of these tools are temperature limited to about 180 C. Some of them, some companies have done some specific work to push that upward on some tools. 200 C is just about max. 300 C is the definite max. And these are for very select tools. So it would be excellent to enable all of them as high temperature as we can get. All right, so in sum, we need to harden tools across all three: characterization of the resource ahead of time, drilling and completion, and operating, monitoring, and maintenance. All right, so let's do some quick case studies. I know let's fly because I'm running out of time. So just to get your ideas thinking about some of the, an example of what could be really cool in a competition like this to think about. The tools that I mentioned that help give you information, right? So MWD and LWD, they tell you things like what pressure your drill string is encountering, how hot it is, what the shocks are, what the vibration is. And also, in the oil and gas context, where the oil and gas is. It tells you a lot of really interesting information. But all these things need power downhole. You have to have energy to make them work. And so currently in the oil and gas industry, they do that with lithium thionyl chloride batteries, either that or a turbine generator. Now, they both have weaknesses. Downhole batteries are a little scary. They are volatile. They catastrophically fail at high temperatures, so nobody wants to push them, push the envelope. When you have a catastrophic battery failure downhole, you can take out easily $1 million worth of tools. So this is just not something that's even considered to push. But what we need to think about is how to skin the cat differently, right? So thinking about different types of batteries that are more stable at high temperatures, shock and vibration, that can be engineered to a form factor that is accessible for downhole use. That could be really interesting from an additive manufacturing standpoint, and it could be really impactful when it comes to being able to power tools downhole. Same thing about other sources of energy, right? So, and I think if there's drillers on the line, oftentimes, and you'll probably laugh when I say this because drillers think that these types of things are sci-fi often. But this is the exciting thing about competitions like this. You bring together a lot of disciplines and different types of people to work on problems, and you can come up with really exciting things. But if you're thinking about needing energy downhole, the thing that oil and gas industry uses, if they're not going to use batteries, is a turbine generator, and that generator is driven by the circulation of the mud downhole, right? But again, temperature limited because it has elastomer seals and other things that we'll consider in the next study. But think about this. I mean, there may be alternative ways to produce energy downhole that you could consider thinking about from an additive manufacturing standpoint. Things like thermoelectric generators, vibrational energy generators, different angles to tackle the problem, which is how do we get energy downhole to power these tools that is not going to fail at high temperatures and horrible, harsh environments. Another real pain point that's worth highlighting is the need for either higher temperature seals or no seals at all. And I can't overstate the problem here, because nearly every single tool I've mentioned in this talk to some extent has a seal that melts at high temperatures, right? And what you have when you have a tool with a seal that melts is you end up with fluid intrusion, and it breaks your tool. So if you look at this on this picture on the left, this is a seal, elastomer seal. And this is a seal after 50 hours at 300 degrees Celsius, right? So that is catastrophic failure. That can't happen because your tool will break. So this is a really interesting project that was actually funded by the GTO. I wanted to throw it out there. This link is the final public report. It was a Baker Hughes project that redesigned a variety of systems, power systems for MWD, and they considered seals as one of the things they tackled, and ended up with a metal on metal solution to a motor. And so it's a beautiful example of what can be done when you slice a problem up. You figure out a small piece, you re-engineer it to work better at a higher temperature. You eliminate the problem. That you can see here, they used additive techniques to prototype some of their pieces. So it's a really cool example. Okay, so to wrap, for each tool that we need to use, right, we need to just walk through a couple of questions, and I think you'll arrive at a cool project for the competition, right? So for every tool that we want to enable, how does it fail? What causes it to fail? Then next, can you fix it with additive? So can it be re-engineered, leveraging additive manufacturing, and iterated quickly? And then next, does it matter, right? So I would pick the low-hanging fruit, the stuff that would have the maximum impact, and try that. The stuff that really will be enabling if you were able to do some performance improvements on it. Okay, so I'm out of time. Thank you very much, y'all, and I'm happy to answer questions on details if you have them.
Perfect. Thank you, Jamie, very much. That was a fantastic overview. We have a couple minutes here available for questions. I do want to recognize, though, that if folks are interested in joining the next session's worth of talks, we will be transitioning here in a few minutes. So within the chat, I think we do have at least one question here. It looks like Scott has the question, and possibly Jamie, this may be a good one for you to tackle if you can. What is the approximate or range of downhole power needs for these types of tools?
Yeah, so the higher power, the better. I just put my contacts information. So for instance, it depends on what you're using. And this is another level of detail that we didn't have time to get into, but I'm happy to chat about it with folks offline since we're time limited, so email me. But for instance, there's EM telemetry, which is a way that you can beam data to the surface, and you can avoid using a mud pulsar, which is a different topic. But EM telemetry struggles in some formations, and the deeper you go, the worse this gets. In a former life, I dabbled in ultra capacitors downhole because they were high power, and they were able to tackle some of these things. So it depends on the system you're interested in, and it depends on what you want to enable. There's a broad range. So email me, and I can send you some more detailed information about that, and we can dig in a little further if you have questions.
Great. Trying to access the chat.
We had one more question that was why we needed batteries and could not just get a wire down there.
Right.
Okay. So this is the subject of a lot of debate in the oil and gas industry. You know, the concept of trying to do wired pipe while drilling. The short answer to that is drill crews are very rough on technologies in the field. And wired pipe, particularly where you thread it together, is very, very delicate. So what you end up happening, it's an expensive technology. There are companies that have developed it, that have worked on it, that tried it, and it got destroyed in the field. Either that or the connections didn't meet up properly and it didn't work. So yeah, if you've got good ideas that can solve that, you know, that can skin that cat, go for it. That's a beautiful, beautiful idea. It's something that could be enabling, but that has not been successful yet.
We had somebody else in the chat saying that with all the robotics that NASA is starting to work on for drilling the moon, there's a potential for a big collaboration between the Artemis project and geothermal in the next 30 years or so. So Dell owner, I recommend you reach out to Jamie and start that conversation. And if there's something that's going on that would be useful as an innovation, push it forward for the Geothermal Prize.
Totally.
Otherwise, we're going to need to wrap up in about the next 60 seconds.
Yeah, so I'll just note about that NASA installations are really cool. So if you can insulate tools and help them perform better using NASA stuff, do it. It's a beautiful idea. So wherever you can find interdisciplinary collaborations like that, it's a great way to go.
Perfect. Well, thank you, Jamie, and thank you, Kate, for both of your perspectives. I thought that was a fantastic overview. Up next, as Tim was pointing out, we have our next session at the top of the hour, Industrial Additive Manufacturing 101, Building Solutions from the Bottom Up. That will, Tim, I believe, require a separate link to log into, so you won't be able to stay on this one. But as long as you signed up for that session, you should be able to access the link via the invite that was sent separately, and as well as now in the group chat. So please join us in a couple minutes, and we look forward to continuing the conversation.